Hello friends, we are starting a new lecture series on the topic electricity and electronics. In this lecture series, this is the first video. So today we will see some of the basic aspects of electricity. Particularly we will slowly construct what is charge, what is the meaning of it, Coulomb's law, electric field, electric flux. You will see some basic ideas of these things alone in this video. Here, title reads Electricity and Electronics. We should understand what is electricity and electronics. There are two terms. One is electricity. Other term is electronics. What does it mean? See, we are having different types of materials like metals, table like wooden things, silica like other materials, sand like materials. So I have given three different examples. So these are the materials, solid materials. And we know that either metals or wooden things or silica or sand, all these are made up of atoms. So all are made up of atoms. So if you look into it, atom has a central nucleus and which contains neutron and proton. Both are present in the central nucleus, and there are circular paths. According to classical theory, there are circular paths in which electrons are revolving around this nucleus. You can say like this. Okay. So, this revolving electrons is filled in different orbitals in a particular manner. You can say that it is filled with the formula 2n square if you recall. Fine. Now the point is, this outermost there is an outermost orbit where the orbit may be filled or unfilled. You know, each electron is having a binding force with nucleus. So each electron in different orbits are binded with the nucleus. So this binding force will be weaker when you go out from the nucleus. That is, the force between these two, nucleus and the inner orbit, is higher when compared with the force between the nuclear and outer orbit. So in the outermost orbit, that is called the valence orbit, where there are electrons. Now that electrons having the weak bond with the nucleus. Now depending upon the atom, this, when you consider metals or wooden things or silica, due to this outermost electrons, the property will be vary. One considered material may have excessive free electrons in its outermost orbit, or it may have completely filled state, or it have very few electrons that are free, or you can say that no free electrons at zero state, zero temperature, no free electron at 0 Kelvin, but there are some electrons at higher temperatures. So based on this electron availability in a material, you can classify a material into conductor, insulator and semiconductor. So conductor is a material like metals, human body, etc. It has more number of free electrons to move within that, so that an electron will move one point to other point. If you are having a metal rod, say this is a metal rod, an electron can move from point A to point B freely. In that case, it is said to be conductor. And some materials like rubber, glass rod, these are the things, wooden table, these are the things where there is no free electrons to move from one point to other point, so that they are termed as insulators. Metals are conductors, wooden things are insulators. And there are third category where the electronic state is filled and there is no free electrons if it is at 0 Kelvin. But if you supply some heat, which means some external force, some energy in the form of heat, in the form of phonons, you can say technically, it will excite some of the electrons from its outermost orbit to the free electrons, so that it will behave like a conductor. It's a partial conductor, so you can call it a semiconductor. So it is called silica. And if you have, listened carefully, these classifications are made with the movement of electrons, whether the electrons are available to move or not. Now, here, the electricity that can be defined as, it is a branch of physics that deals with electrons, or in general you can say that deals with charge. See here, what is electron? In an atom, electron is assumed to be negative. When we are talking about electron, it is said to be negative. If you are talking about proton, it is said to be positive. Okay? Right. Fine. Here, all these electrons as a property. It's like, you see, as like, if you are having a water, right? Assume that in an analogy, assume that there is a tub which contains water, right? Now, we can say that for a water, we can say potential energy, kinetic energy, like things. When this water tank is moved upward from a ground level, then you can talk about the potential energy. When the water is flowing from one portion to other point, one point to other point, suppose we are connecting with a tube and it is flowing from this point to another tub in the bottom. If the water flows here, then we will talk about the kinetic energy, right? Similarly, if we talk about an electron, right, it has a charge. We will say a property called the charge. charge is a property of electron, you can say. It's a property of electron. You can express in terms of proton as well. Now, electricity is a branch that deals the charge and its characteristics. See, as we said, charge is a property. Now, we study this property under various situations. Various situations. What are the situations? Situations where this charge is under rest always. When the charge is stationary. When the charge is stationary, or when the charge is moving, and a charge is under certain circumferences, certain situations. For example, whether the charge is under spherical conditions, there are certain situations we will discuss later. So broadly, if the charge is stationary, that is, if you are considering a charge which is not moving at all, it is remained rest in a position where it started, right? So that is called, if you study such cases, then you can say that electricity, in that you have a specific branch, electrostatics. Electrostatics is a sub branch of electricity that deals with the charges of stationary state or rest state always. Another case, suppose if the charge is moving, in that case we can say that electrodynamics or current electricity. This deals with the properties of charges under moving condition. Properties of charges under moving condition. Well, so in the nutshell, what is electricity? Electricity is the study of charges under two cases in a broad sense, when the charge is at rest or when the charge is at moving. Okay, that is for about electricity. But then what about electronics? Here also we will study the property of charge, property of charges, but within different electronic components. Different electronic components. For example, we are having transistor, we are having FET, we are having operational amplifiers, we are having diodes, light emitting diode, Zener diode. There are different types of circuits. We have an inverting amplifier, non-inverting amplifier, and there are a lot of circuits which we can construct using the composition of circuits. Charge flowing through a capacitor, charge flowing through an inductor, all these things. If you study the property of charges, right, and within the different electronic components and how these components are behaving if you apply charge into it, so these are the things that comes in electronics. Generally, electronics is a branch which studies the charges and the components which deals these charges. So this is what the title. Now we are going to see some theories related with electricity and some of the aspects related to electronics. Basically, this course is for an ancillary physics level of chemistry and math students of undergraduate programs. So in that level only we are going to cover. So what is charge? Charge is a property. It can be said to be positive or negative. Charge can be positive, charge can be negative. Assume that it is a point charge. Let us say this is a point charge. If it is positive, then this charge, right? Assume that if it is a point charge, it has some property. Here, say for example, this will exert a force. It will exert a force. If it is a positive, then this line of forces pointing outward from the point charge. Suppose if this point charge is a negative, then this line of forces will pointing towards the charge. So this is the reason. Charge that exerts force always, and this force lines are going outward when it is a positive charge, going inward when it is a negative charge. So here it is, the lines are outward, here the lines are inward. Due to this, right? And the force lines are going outward, it is called positive charge. And the force lines are going inward, it is called negative charge. Due to this, you can say that the properties of charges as you can define the properties of charges as point number 1. Like charges repel. It's like, see, I am pulling outward and another person, he is also pulling outward. So if we both pull outward, what will happen? We cannot pull further, right? So we will went back, right? If two forces are pulled, then what happens? It will repel back. In that way, if you bring another positive charge close to a positive charge which is already present here, what will happen? This exerts an outward force. This will also exert an outward force, so that it will be pulled out. It will be repelled out, so that when it comes towards this, both cannot attract each other, both cannot mingle with each other, rather it will go away. That is, like charges repel. This is true for negative charge as well. This is true for negative charge as well. Okay? Because this force lines will go into this force lines will go into this both cannot be put together. So like charges will repel. And unlike charges, positive, negative will attract. Unlike charges will attract. Another thing, the line of forces are uniform in all directions. See, it is the line of forces, it acts on all directions, all three directions. If you consider the Cartesian coordinates, the line of forces are uniform in all directions. So this is about charge. Fine. Now, assume that we have a point charge here. Let us say Q1. We have another point charge here. Let us say Q2. According to the properties of charges, like charges repel, unlike charges attract. Assume that we don't know whether these two are like charges or unlike charges, whether it is positive charge or negative charge, or one positive, one negative, that we don't know, right? And the distance between them is r, but it will exert a line of force, either outward or inward. So this will also exert a line of force outward or inward. Now we can write the force between these two charges. That we can write the force is directly proportional to the charge Q1. The force between these two charges is depending upon the charge of Q1, and it is also directly proportional to the charge of Q2, and it is inversely proportional to the distance between them. Collectively, you can say that F is proportional to Q1 and Q2, inversely proportional to the square of the distance between them. Okay? And this proportionality constant is replaced with 1 by 4 pi epsilon naught Q1 Q2 by R square. And this was discovered by Coulomb, so that it is called Coulomb's law. So according to Coulomb, if you place 2 point charges whose charge, whether it is positive or negative, is unknown, irrespective of charges, if you place 2 charges in a distance r from each other, then the force acting between these 2 charges can be written as F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, where Q1 is the charge of this point charge, Q2 is the charge of another point charge, and R is the distance separating between these 2 charges. Here, this term epsilon naught, it is called permittivity of free space. What do you mean by permittivity? The ability of the medium to allow the electric fields into it. Electric fields into it. This epsilon tells us the ability of the particular medium, how capable it to allow electric field into it. That is permittivity. If you put 0, then it is the epsilon naught, it is the permittivity of free space. And you can put this epsilon with one another suffix for different mediums. The permittivity of the air is more or less close to free space, whereas the permittivity of other materials like water or metals or like that, the permittivity will vary for different mediums. Right? Here, the permittivity of the free space can be written as 8.854. So epsilon naught, which is equal to 8.854 18 into 10 power minus 12 Coulomb square per Newton meter square. Or you can say that the unit will be Fermi per meter. The unit will be Fermi per meter. See, for this case, now we have proportionality constant 1 by 4 pi epsilon naught. If you substitute epsilon naught here, 1 by 4 into 3.142 into 8.854 18 into 10 power minus 12. If you evaluate this, this will yield you 9 into 10 power 9. And this is the constant. Right? It is proportionality constant. It does not have a unit. It is the constant. Okay? Fine. Assume that. Suppose we are having the charge 1 and this charge is also 1. Both are same, which is separated by 1 unit distance. R is equal to 1. In that case, R square equal to 1. If two like charges, either positive or negative, two like charges are placed with an unit distance, then what will happen to the force? The force becomes 9 into 10 power 9. Q1 becomes 1, Q2 becomes 1, distance is 1, so that 1 square 1, it becomes, force becomes 9 into 10 power 9. The unit for force is Newton. Okay? It's a one simple trivial case. But from this example, we can define Coulomb. We can define Coulomb. Coulomb is the unit of the charge. He said charge is the property and it has a unit which is called Coulomb. So, charge, it has the unit Coulomb, it is denoted by capital C. See, Coulomb can be defined as, 1 Coulomb is defined as, suppose if there are two like charges Q1, Q2 which is placed with an unit distance R, then if the force between these two charges is equal to 9 into 10 power 9 Newton, then these two particles having the charges of 1 Coulomb. Right? How it is defined? We created a situation. What is that? We have a like charges, equal charges placed with the distance R. That is placed with the distance R, which is unit distance. If these two charges placed with the unit distance, now if the force between these two charges is 9 into 10 power 9 Newton, then the charge, it was unknown, right? This charge, now we can say that each having 1 Coulomb of charge. So this is one definition of Coulomb under the case of electrostatics. Suppose in the case of electrodynamics definition, in electrodynamic case, assume that this is a wire. In this wire, current is flowing, that is electrons are moving from one side to other side. Now 1 Coulomb is defined as if 1 ampere of current is flowing into the wire for 1 second, then it is called 1 Coulomb. Right? So Coulomb, which is equal to ampere per second. If the electrons are moving, in that case electrodynamic definitions are coming. Right. Now assume that in this place, now we have been telling that point charge, but what is there in that we didn't mention so far. assume that in this place there is an electron. Now, what would be the charge? The charge of electron is equal to 1.6 into 10 power minus 19 coulomb. This is the charge of electron. Okay. And if you want, what is 1 coulomb? If you want 1 coulomb, you bring, right? You can rewrite this. Fine. Suppose, if you write, 1 coulomb of charges, which is equal to 6.241 into 10 power 18 protons. Okay. Suppose if you are considering protons, then if you sum up the charges of 6.241 into 10 power 18 protons, that will constitute 1 coulomb of charge. So this is coulomb. And here, let's move to the definition for electric field. And before understanding what is electric field, let me come with an analogy. Assume that here we are using some wood materials and fire it up. So there is a fire created here, right? Suppose if a person from infinite distance moving towards this fire, when this person moves towards fire, when he is going towards it, he experiences some hotness, right? Fire is, exists only here. So this fire, it is glowing here, but in this area nothing in it. But if you are going towards that, you can experience a hotness. That hot temperature you can feel, right? Even though nothing in it. Which means this fire that exerts heat in the surrounding, which felt up to certain close proximity. At a larger distance, here the hotness will be less, here the hotness will be higher. When you go from an infinite distance towards the fire, the hotness will increase gradually. When you go very close, you can feel the unbearable high temperature, right? This is the case we all might have witnessed. Everyone might have witnessed at one point this situation. Assume a similar situation if there is a charge, right? If you bring another charge from infinite distance towards this charge, we already told that this charge exerts some force. Okay? It exerts some force. Now, this force cannot be realized when the moving charge is somewhere at very large distance. But when it is moving close to it, it will experience that force. Right? Assume that there is a proximity within which the force is experienced. That area, in that area, you can define it as field. Right? This electric field is an area within which the force exerted by this stationary charge is experienced by the moving charge. Right? Now, how to define that? Electric field is denoted by E. Okay. Now, this E is denoted by E is equal to F by Q, where F is the force exerted by this stationary charge. Let's say this is Q naught for understanding, and moving charge is Q. Now you can say that electric field E as force by Q. These are the vector quantity actually. Field is direction oriented. Why? Because when you going towards the field, and when you going towards the stationary charge, the field will be maximum. When you going away from the stationary charge, the field will be slowly decreasing. The field will decrease. So it's a vector. Now, what is the formula for force? Right? See, in previously, the force between two charges or the force experienced by the charge, that we have written as using Coulomb's law, F vector which is equal to 1 by 4 pi epsilon naught Q1 by Q2 by R square. Apply here. Here, this interacting two forces are, one force is Q naught, other force is Q. In that case, if you substitute the formula for F, you can write 1 by 4 pi epsilon naught Q1 Q2 by Q naught Q by R square divided by Q. So this and this will goes out. So that now electric field E, which is nothing but Q naught by R square. What this formula tells us now? This field E will depending upon the charge Q naught. If the charge of this stationary charge is high, then the field will be high. And this field will decrease when you increase the distance. Right? Suppose if I am measuring the field at this point, this is R1. Another case, if I am measuring the field at this point R2. What would be the field at this point? The field E1 at the distance R1 from the point charge is higher when compared with the field E2, which is measured at the distance R2 from the point charge. Why? Because the field is square of the, inversely proportional to the square of the distance from the charge to the point where it is measured. So field will be higher. No, the field is increasing when you increase the charge of the stationary charge, and if the point at which the field is measured, in that case the field will be decreasing if you increasing the distance. This decrease will be in terms of square of the distance between that. So this is how you can understand the electric field. So electric field is nothing but the force acting on a moving charge. A force acting on a moving charge. Fine. Now you can define the unit for electric field. Unit for electric field is, for charge it is Coulomb. The distance square, that is, you can say meter square. So that Coulomb per meter square you can say, or in simple words you can write the unit for force is Newton, for charge it is Coulomb. So you can write Newton per Coulomb. It has another unit as well, volt per meter. So there are two units, Newton per Coulomb or volt per meter. But you have now electric field due to a point charge. See, assume that the entire thing is happens in vacuum. We create a situation where there is a point O and another point P. At point O there is a charge Q. It's positive charge, assume that. At point B we place a test charge. So this is a test charge. We are placing. Now the distance between this 2 points, OP is R. The everything is at vacuum. Under this condition, what would be the electric field E at this point due to this charge plus Q when a test charge Q not placed here? This is the question. This is nothing but, if you write the equation for force according to Coulomb's law, you can write 1 by 4 pi epsilon naught Q naught by R square. Now, as per the definition, the electric field is nothing but force per charge. Here the charge means you have to apply the test charge, so it is Q naught. Now, this equation becomes 1 by 4 pi epsilon naught Q by R square. So this is the electric field E at this point due to this charge Q when the test charge Q naught is present at this point. Okay, fine. Now, here if this charge is positive, then the line will be going towards outward direction. The charge is negative, then it will be the direction will be inward. That is the thing. So that electric field E due to a point charge Q naught placed here, test charge placed here, and another charge is placed here. Because of this charge, when a Q naught is present here, an electric field experienced at this point can be written with this equation. Flux of the electric field. Let us consider another situation. See, there is a situation where we have electric field lines. Electric field lines may not be uniform if the charges are in this side, and if this is the positive charge, so that the lines will moving outwards. Assume that such non-uniform electric field, non-uniform E say, there is a field where non-uniform. Now you consider a plane, right? You can consider a plane along these force lines, or you can consider plane perpendicular to these electric field lines, or you can consider a force line which is inclined. We have considered one such inclined plane. Assume that this. So in this case, this force line penetrates this plane, that is electric field line penetrates at this point, right? Now see, one line is penetrating here, there is another line which is penetrating from here, there is another line which is penetrating from here, there is another line which is penetrating. So likewise there are n number of lines coming out of this considered plane. Now you can define flux is number of electric field lines passing through a given surface. Passing through a given surface. Now how to write the expression? Let us consider this line for convenience. And let us divide the surface into infinitely small squares. Now consider this square, right? So there is a square that we have considered. Within this square, let us assume the electric field is uniform, because this is an infinitely small square. So we have considered an infinitely small square. Within that, the electric field is the electric field is uniform. Now see, so this is an inclined plane and it's a small square in that. So this is the direction of E vector, and this is nothing but normal, that is perpendicular line from this plane. It is the perpendicular line from this plane. That is, the electric field lines are going and the plane is putting like that. If you draw a line from this, it will go like this. So this field line is here and it is going like this. There will be an angle between this, that you can write theta. Fine. Now if you straighten this, you can draw the square like this. So this you can name it as ds. In that case, this become ds and this line become E if I straighten this. Okay, and this is theta. Right? Now we can write the flux phi at this point. The flux phi at this point is equal to, this all are vectors, so E vector into here, this ds is nothing but the area component, small area component of this small square, so ds, right? The entire area of the surface you can write S. Within this is the small area, and the component ds is a component which is normal to this small area. Okay, fine. Now if you remove this vector, you can take a triangle, trigonometry for your help. So this is hypotenuse and this is adjacent side and this is opposite side. And what is that? Theta is between adjacent side to hypotenuse, so that you can write adjacent side by hypotenuse, which is equal to cos theta. So you can write phi, which is equal to E ds cos theta. Okay, now you can define this as d phi. Why? Because we are considering flux for this small square, but we have n number of such squares, so this is d phi. See, now if theta equal to 0, d phi becomes E ds. Suppose if theta equal to pi by 2, what will happen? D phi becomes 0. And if theta is equal theta greater than pi by 2, d phi becomes less than 0. If theta equal to theta less than pi by 2, d phi greater than 0, but less than 1. Okay, greater than 0 but less than 1. What does it mean? When this plane is along the electric field line, then you can define d phi is nothing but the field multiplied by the component. If it is perpendicular, right? In that case, if the pi by 2 is perpendicular, when will be perpendicular? When it is perpendicular actually, see here, if the lines are going like this and if you are putting the plane like this, and the normal will be perpendicular, right? In that case, no line will penetrate through this plane. The line will be flow on the plane, but it will not penetrate, right? So in that case, what will happen? If the theta is pi by 2, that is this line and the normal component has 90 degree, then flux is nothing but the number of lines passing through it will be 0, right? If you put like this, so this is the direction of the electric field and this is the direction of the normal component. It is 90 degree, then no line will be penetrate through this plane. That is the case for this. And when this angle between this is 0, that is, if you put the plane perpendicular to it, now this is the direction of the E, that is electric field lines E, and the normal component also will pass, in the same direction. This is the normal component of this plane. Both are in same direction, so theta will be 0. In that case, all the lines will pass through. So where we have the product of EMS, this case. And for other cases, for the inclined positions, we have the cases like this. Now, but d phi is for only this small square. If you want the number of flux lines through the entire plane that we have considered, in that case, you have to integrate this d phi for the entire sphere, entire sheet. In that case, this is E ds cos theta. E ds, integral of E ds. Here, closed integral is for the entire case. That is, if this is the sheet plane, then you can put integral. Suppose instead of a sheet, if we have considered a sphere, that is, for example, this is the electric field line. In that, you have considered a sphere within this. There is a sphere. In that sphere, if you consider one, this is a sphere. So in this, if you consider only a small area. Now, if you want to extend the electric field line for the entire sphere, sphere is a closed environment. In that case, you have to write closed integral. When you consider sphere in the place of a plane. If you consider sphere in the place of plane, you have to put a closed integral. Circle represents the closed integral. Right? Now, what is the unit for that? Unit for E. Unit for E is nothing but force per charge. Newton per Coulomb. And now, for surface component, area component, it is meter square. So that Newton meter square by Coulomb. The unit will be Newton meter square by Coulomb. That is what you can write. Or earlier, for E we can write volt per meter. Now, if you rewrite this, for here volt per meter into meter square, it will be voltmeter. The flux, the electric flux, the unit of the electric flux will be Newton meter square by Coulomb or voltmeter. You can write. So in a nutshell, what is flux? Flux is the number of electric field lines passing through a given surface. How did we arrive this? See, we have considered electric field lines in a plane, where we have considered another plane that is inclined, and we have divided into n number of small squares. This entire field is non-uniform electric field. Within this small square, we assume that it is a uniform electric field. We have written an electric field component in this direction. A normal component to this square is ds, that is area component. The angle between that is theta. With the help of trigonometry, we can write d phi, right? With the help of d phi, we can write E ds cos theta, and from that we have inferred that when this electric field lines, when we consider a plane, if the plane is along the direction of the line, then there is no field will pass through it. If it is perpendicular to it, then maximum number of field will passing through it. The flux is high, and if you have an inclined positions, and we have the conditions, we have the statements. And as we have calculated the expression for a small square, and we have integrated for the entire plane, we will get the total number of fluxes. If it is a closed surface, we have to take closed integral, surface closed integral over the open integral. This is the case. So in this class we have talked about what is electricity and what is electronics, what is charge, Coulomb's law, electric field and flux of the electric field. These are the topics that we have covered in the level of ancillary physics. Fine. Let us continue in the next class. Thank you. Bye bye.